Hello students, let us continue the discussion on moving charges and magnetism. And today we are going to connect magnetism with electrostatics in a deeper way, in a basic way. So in the last class, we obtained the expression for the torque experienced by a rectangular coil placed in the external magnetic field, right? The magnitude of torque is given by I is equal to mb sine theta. In vector form, it was given by vector tau is equal to vector m cross vector b, m cross b, where b is the magnetic field, m is the new term that we introduced in the last class, which is called magnetic dipole moment. Magnetic dipole moment is the new term m, which we introduced so that the torque experienced by an electric dipole and the torque experienced by a rectangular coil looks alike, because there it is tau is equal to P cross E, magnetic electric dipole moment cross electric field. Here torque is tau is equal to m cross P, where m is magnetic dipole moment and B is the magnetic field. So now we shall see what is this magnetic dipole moment and know more about it. The mathematical expression for that is quite simple. It's NIA, and this M will have the same direction of A, which can be taken using right hand thumb rule. And now we shall see this magnetic dipole moment. Whenever we have magnetic dipole moment, the word dipole comes into the picture. What is a dipole? Where you have dipole, two poles. Di stands for two, right? Two poles. So when I say electric dipole, there we had two basic polarities or poles. Okay, poles is the short form for polarities. Two basic polarities in electrostatics, which are the charges, isn't it? Charges makes the basic elements or elementary particles or elementary, we can call it as quantity, okay, elementary quantity in the electrostatics, charges, right? That is where everything starts from. A charge, then everything builds up, force between charge, electric field due to charge, electric dipole, torque on that dipole. So everything is dependent on the basic elementary concept or elementary uh, uh, this elementary particle, which is charge, right, or elementary quantity. But now there it was well and good. When I say electric dipole, it was two equal and opposite charges separated by certain distance. Everything else is done. That's it, very simple. So we had two poles, positive pole, negative pole, separated by certain distance, and hence we named that as electric dipole. And after defining electric dipole, we went for electric dipole moment, P. But here we have not yet seen a magnetic dipole, but in order to get the similarity, we have directly introduced the term magnetic dipole moment, isn't it? There in electrostatics, we first defined electric dipole, then we defined electric dipole moment. But here we are encountering or seeing magnetic dipole moment itself as the first term, and now we shall see what is magnetic dipole, isn't it? Because there it's the opposite way, but now magnetic dipole has to be defined. Let us see how to define magnetic dipole. Before defining it, we should visualize how does magnetic dipole looks like. Because when I say electric dipole, it is positive and negative poles or positive and negative charges, which makes an electric dipole. But here, how does or what are the 2 poles of a magnet, of a current carrying conductor? Where does we, how can we visualize that? The questions can be answered now. So basically, uh, as similar to the positive pole and negative pole of electrostatics, here in magnetism we have a north pole and a south pole. Okay, that is where the concept of pole starts. Okay, now is the time to start the concept of pole. So how does they look like? Where do they exist? This north pole and south pole of a magnet originates from a single current carrying conductor. Okay, a current carrying conductor, okay, a single coil of current carrying conductor constitutes both the poles of a magnet. Both north pole and south pole can be seen in a current carrying conductor. Okay, so this is going to be a little tricky, okay, but you can imagine it, nothing to worry. Say you have certain current flowing through this kind of circular coil like this. Okay, like this, current flowing through like this. Now uh, just a minute, let me bring you the same kind of coil and show it to you. Right. So here I have a similar kind of coil of say 2-3 turns. Uh, and if the current is flowing in the same way like this, okay, then what is the or how do we see the magnetic poles in this current carrying conductor? See, the logic that we should be making use is there are two ways of remembering the poles. Okay, so, yeah, the poles are named as north and south, right? You know that. But now you will have the perfect clarity what is the basic source of a pole of a magnet, poles of magnet, because both the poles exist in the same current carrying conductor, current carrying loop particularly. Okay, but which pole should be, which side should be taken as north pole and the other side will be south pole? Okay, that should be decided now. Okay, basically a current carrying conductor, a single current carrying conductor constitutes both the poles of a magnet, and one pole shall be seen on one plane of the magnet and the other pole shall be seen in the opposite pole, in the opposite plane of the same current carrying coil. So now the logic is electric field lines always start from north pole. Okay, very similar to the electric field lines which start from positive charge end at negative charge. Similarly, magnetic field line starts from north pole and ends at south pole. So if this is the situation and current is flowing like this, okay, like this, now what is the direction of magnetic field? Right hand thumb rule. Okay, so like this, and hence the the direction of magnetic field is like this, which means the magnetic field is going away from the coil like this. So this acts as the north pole of the magnet. Okay, or magnetic dipole I can call. Okay, so a current carrying conductor itself is a magnetic dipole. Okay, keep that in mind. So now this phase, since the magnetic field starts from the coil and moves away like this, so this phase acts as north pole, and current is still flowing like this. What about the direction of magnetic field in the other part? So in the other part, the direction of magnetic field is like this, right? So the magnetic field would be entering the coil like this, okay, entering the coil away from it like this, which means this is the plane to which the magnetic field is entering or ending. So terminating. So I can call this phase as the south pole. Okay. So this is one logic to remember. A current carrying coil acts as a magnetic dipole which has both north pole and south pole in the same coil. One of the plane acts as north pole, and the other plane, the opposite plane of the same coil, acts as the south pole. The plane from which the magnetic field lines are moving away acts as north pole. The plane to which the magnetic field lines enter or terminate at is considered as south pole. And this is one logic. The other way of remembering the poles of a current carrying coil is as such. So if the current is flowing like this, then so look at this, you can make a shape out of it like this, right? This kind of shape. Okay. So this is how the current is flowing, right? Now, if I look at the same coil from this side, okay, for me, the current is now flowing like this, right, in the opposite way or in the clockwise direction. Here it is in the anti-clockwise direction, and here the current would be in the clockwise direction like this. The same one, the same coil when I look like in the opposite plane, it looks somewhat like this. And now I can still do the same kind of pattern like this and join them. Okay. So now, as you can observe, this shape, okay, when you have this kind of shape, as you can observe, this shape is very similar to the English alphabet N, the capital N, and this is very similar to S. So when the current is flowing like this, yes, it's obvious that the magnetic field lines would come out of it like this. So this kind of pictorial representation will also help us in remembering the magnetic poles, north and south. Okay. So if it is like this, field lines are coming out of the board or out of the plane, and hence this is north. So you take this, it's clockwise, and the field lines will be entering it like this. So this must be south. Either through right hand thumb rule or through this kind of pictorial representation, you can remember the poles with respect to the direction of current. Clear with the concept? Similar to electric dipole, where we have two poles, positive and negative, here also we will have two poles of magnetic property. One is north pole and the other is south pole. Unlike the electrostatics, here both the poles of magnets, both the poles of the magnet can be found in the same coil. Okay, the very same coil constitutes both the poles of the magnet, both north pole and the south pole. And the decision of north pole and south pole shall be made by observing the direction of current in the coil. One way is right hand thumb rule. If the field lines are going away from the coil, then it is north pole. If the field lines are moving towards the coil, then it is south pole. And this is how we can remember the north pole and south pole diagrammatically. Okay, the same coil. These two are the same coil, weaved from this side once, okay, and this side once. So this side, if it has become north pole, and hence the opposite face would definitely act as south pole. Okay, so this is about magnetic dipole, which arises from the same coil. The two poles are north and south. Yeah, the reason for naming north and south poles shall be studied in the next chapter. Okay, nothing to worry about that. Yeah. Now we shall define magnetic dipole moment. Okay. How do we define? We need some physical effect to define it. Yeah, here we have already set the formula, and we'll make use of this formula to define m here. Okay. So according to this formula, m becomes equal to tau by b sine theta, right? Now, m becomes equal to tau when b is 1 Tesla and theta is 90 degree, right? Sin 91, b is 1 Tesla, and hence m becomes equal to tau. So using this condition, we shall now define m. So magnetic dipole moment is numerically equal to the torque experienced by a magnetic dipole. What is a magnetic dipole? See, from now onwards, whenever I say magnetic dipole, it is nothing but a current carrying coil of any number of turns. That doesn't matter. Okay. But basically, when I say current carrying, when I say magnetic dipole, it is a current carrying coil itself, nothing else. Okay, experienced by a magnetic dipole uh, held perpendicular, held perpendicularly, held perpendicularly with the magnetic field, with the magnetic field, external magnetic field. It is external with the external magnetic field of 1 Tesla. Okay, so this is how we can define magnetic dipole moment, M. Okay, so I hope you now have the clarity of magnetic dipole moment, which are the two poles. How do we get to know about each pole, and the definition of magnetic dipole moment. And when we concluded the expression for torque experienced by a current carrying coil, the shape of the coil chosen was rectangle, isn't it? You can remember the diagram. Okay, so the shape of the coil that was chosen is rectangle, right? Rectangle shaped coil of area A kept in external magnetic field B, with the current flowing through that equal to I. But this is not necessarily a required shape. Okay, so now we have an expression for torque experienced given by M cross B. What is M equal to? M is equal to Ni A cross B, right? So here I is the current, A is the area of the loop. So now, since we have the area of the loop given here, it is not necessary that we must have a rectangular shaped coil. We can have a coil of any shape. So, as I say, I can have a coil of circular shape, I can have a coil of triangle shape, any shape that I need. Okay, I can take a coil of any shape and pass current through that. And the area of that shall be taken here to simplify. Okay, these areas would be important for us to simplify them here and get the expression. Clear with this? So now I have generalized the expression M cross B, which was derived only for rectangular, derived using only the rectangular shaped coil. Now I have generalized that to circular, triangular, or any kind of any shaped coil. The only condition that we should have is the coil should have the area. Okay, the area of the coil itself should be chosen as A and kept into the expression, and hence we'll get the torque experienced. Okay, and now we shall see a few cases, the special cases of it. The magnitude of torque experienced by the coil is given by mv sin theta, right? Now, the few special cases are as follows. When do we get minimum torque and the maximum torque? Very similar to what we discussed with the uh, electric dipole, right? The same kind of discussion. So, the magnitude of torque is minimum when theta is either 0 degree or 180 degree, right? And then tau becomes equal to 0. That is the minimum torque experienced. And the torque experienced is maximum when theta is equal to 90 degree, right? So it is tau max, which is equal to mv. Okay, these are the special cases, and this is one generalization which you should keep in mind, because that is going to help us in further discussions. Okay, so even when you have a current carrying coil of circular shape like this, kept in an external magnetic field B, and let the current flowing through that be in this direction, and hence the area of direction of area would be like this. Okay, somewhat like this. It's difficult to draw. Yeah. This is the direction of area, this is the direction of magnetic field, and hence the angle between them is this which is theta. So, if I is the current flowing, and the entire area shall be taken to get the magnitude of area, and hence the uh, value of m is given by n I current flowing is A is the area of the loop. Okay. So, even when you have a circular loop like this kept in the external magnetic field, the magnetic moment, magnetic dipole moment of that is given by NIA the same way, where A is the area of the given loop of any shape, okay, of any shape. That is the main point. Now, if you can remember, we expressed the electric field on the axis of an electric dipole, okay. The electric field on the axis of an electric dipole was expressed in terms of electric dipole moment P, right? E is equal to so and so into 2P by R cube. So, in the same way now, what we are going to do is we shall try to express the magnetic field on a current carrying conductor or current carrying loop like this. We already have the expression for this, right? We have derived it, one important expression. Getting the idea? See, when we have an electric dipole, we defined or derived the expression, the standard expression that we had. Positive charge and negative charge on the axis at certain point P, we took the expression for electric field. We derived the expression for electric field 1 by 4 pi epsilon naught 2P by something. So, now in the same way, we now try to express the magnetic field B on the axis of a magnetic dipole, because from now onwards this current carrying loop is not a simple loop. Instead, it is a magnetic dipole. So, when I have a magnetic dipole, I can get magnetic field on the axis of that magnetic dipole expressed in terms of magnetic dipole moment m. Okay. First, let me write the expression that we derived is given by, which we have already derived, is given by V is equal to mu naught by 4 pi into 2 pi I r squared divided by x squared plus r squared to the power of 3 by 2, right, where r is the radius of the coil and x is the distance between the center of the coil and the point where we need the magnetic field. So, now since we expressed electric field in terms of electric dipole moment, now we want to express magnetic field in terms of magnetic dipole moment. Before I go for expressing B in terms of m, I would like to simplify this by considering a special case. The special case is as follows: when, because I don't want to consider a small length of x, I want to move away from the magnetic dipole. Okay. See, so as of now, till now we were considering this as simply a current carrying loop, but from now onwards, this current carrying loop itself is the magnetic dipole moment, right? You know that. So, if I take a point far away from the magnetic dipole moment, or if I consider a very small magnetic dipole moment, which means smaller radius 1, the condition would become x very much greater than r. For this condition, the expression becomes equal to B is equal to mu naught by 4 pi 2 pi I r squared divided by, see, out of these two, x squared plus r squared becomes negligibly very small, and hence the expression would reduce to x squared to the power of 3 by 2. 2 and 2 cancels. So, it is x cube which is left. And now, what I want to introduce here is the term m, the magnetic dipole moment, right? How do I do that? We already know magnetic dipole moment is given by I into A. Right? It is NIA. Number of turns chosen is 1 here. So I can directly write it as IA simply. So now what is A? A is the area of the loop considered. Okay. And what is that area of loop? Since the loop is of circular shape, the area of the loop is pi r squared. So for this loop, m becomes equal to m equal to I into pi r squared. So now you see what happens is mu naught by 4 pi into, look at this, pi r squared into I. Here we have the term, required term, isn't it? Pi r squared is A, I is current. So I can replace these three terms together with m by x cube. That's it. This is the expression for magnetic field on the axis of a magnetic dipole, expressed in terms of magnetic dipole moment. Following? So now B becomes equal to mu naught by 4 pi into 2m by x cube, and the direction of B will be same as of the direction of magnetic dipole moment. Okay, you can observe it carefully. See, at this point, the direction of magnetic dipole moment, the direction of magnetic field is like this. Right here, it is like this into the coil. There it is out of the coil. And what else do we have? What about the direction of magnetic dipole moment? Direction of magnetic dipole moment is also given by the same condition. Magnetic dipole moment will have the same direction as of the area. What is the direction of area? Direction of area shall be again taken by right hand thumb rule. So when I take right hand thumb rule, the direction of area is same as of the direction of magnetic field. So direction of area is same as direction of magnetic field, which means the direction of magnetic moment, magnetic dipole moment is same as the direction of magnetic field. Okay. So this is how we express B in terms of M. This is an important way of expressing B. This expression is very important. Yeah, also you practice the derivation once. It's not that difficult, very easy derivation. Okay. Right. Okay, now comes the interesting topic. Okay. Yeah, these were also interesting, but this is very important one, because now we are going to look in the atomic scale. Okay, in what happens inside the atom, and hence in the next chapter we will study and interpret individual matter or substance as magnetic or different kind of magnetic properties with the different kind of magnetic properties. So the basic thing is, see, what we discussed so far is about a current carrying coil, right? So what is actually a current carrying coil? There were certain charges flowing in that coil with certain velocity in a circular path, right? So whenever we have certain charge flowing in the circular path, not necessarily circular, in any closed path repetitively, there and all, we can expect magnetic field, or we can consider that particular arrangement as magnetic dipole, isn't it? So whether it's a circular coil or a rectangular coil, any kind of coil, if we have charges flowing in any shape, any closed path repetitively, then we can consider that arrangement as magnetic dipole, isn't it? With the dipole moment of I into A. So, if we think deeply, what we can observe is, see, what is every atom made up of? Electron, proton, neutron. You know that, right? Proton and neutron are will be there inside the nucleus, and we will not be worrying much about their motion. Okay, they are almost considered to be stationary now. Okay, they are not actually, but we are not considering the motion of proton and neutron. Okay, nothing to worry about it. They are inside the nucleus, held firmly, situated in the center of the atom. But what about the electrons? Electrons are moving. So electrons are moving in circular paths around this nucleus. What are electrons? They are charged particles, charges. So they are repetitively moving in a circular path, isn't it? So whenever we have certain charge moving repetitively in a closed path, there and all we can call the arrangement as magnetic dipole, right? It's either way, or you can take a moving charge constitute current. Wherever you have current in the circular shape or in a closed path, there and all you can have magnetic dipole. Okay, it's vice versa. But the basic thing is that wherever you have the motion of charge in a closed path repetitively, there and all we can expect magnetic dipole, or we can call that arrangement as magnetic dipole. So for simplicity, I'll be choosing a hydrogen atom because I can have only one electron in that, and I'll consider the revolution of that electron, and I'll see what is the magnitude of magnetic dipole moment, because the magnitude of magnetic dipole moment is known to us. M is equal to NIA for n turns. For one turn it is IA, current into area of the loop. So now we will see what is the magnitude of magnetic dipole moment produced by the revolving electron of an hydrogen atom. Okay, so we will derive the expression for that now. So let me consider the electron, okay, moving in a circular path like this with nucleus situated at its center. Let r be the radius of the circular path. Obviously this radius would be very small, but that radius would be there, small, but it will be there. So let small r be the radius of the circular path chosen by the electron, and v be the magnitude of velocity. Okay, it's not about direction. Direction always continuously changes, but v is be the magnitude of velocity of the electron in its path, and t be the time period of revolution. What is time period? Time taken to complete one revolution. Okay, so these are the conditions. Obviously it's an electron, it will have the charge equal to E, right? E is the charge of electron. It's only about the magnitude of charge which is important for us now. It's always negative, that we know, but we are worried about the magnitude parts. T is the time period, E is the charge, V is the velocity, magnitude of velocity, R is the radius of the path prescribed. Now, the expression for M is I into A. Area of the loop, yes, it is easy to take pi r squared finished because it is a circular path. What about I, current? If you can remember properly, we have actually solved a problem like this and obtained the expression for current. Let me write that. Okay, see, current is given by charge by time, right? So what is the charge that is moving here? It is the charge that is moving here is an electron, which is equal to E, right? And I can take any time. So let me take the time chosen equal to time period itself. Okay, E by T will give me the current. Okay, in so and so time, E is the charge that crossed the point, that passes the point. See, if I take 2t, 2 times the time period, then the same charge passes a chosen point twice. So then I should take 2e by 2t. Since I have chosen the time taken equal to time period, which means the time taken for one revolution, the charge can actually pass a point just once in the time equal to the time period of revolution. Since if it goes on, if I take 2t, then the same charge passes the point twice. So then I should consider it as 2e. Okay, but since for one revolution, this is the condition that we'll be left with. For one revolution, Q becomes equal to E, small t becomes equal to capital T. And now E is easy, that's not a problem. T is what we get to know. Okay, so velocity or the speed or the magnitude of velocity, all of them are same, is equal to distance traveled by time taken. Again, for one revolution, what is the total distance covered by the electron? For one revolution, the distance covered by the electron is equal to the circumference of the circle, which is equal to 2 pi r divided by time taken. For one revolution, the time taken by the electron is equal to its time period, which is capital T. So that's what we have. V is equal to 2 pi r by capital T. And now, what will be this T equal to? And hence T becomes equal to, the time period T becomes equal to 2 pi r by capital T. 2 pi r by V, magnitude of velocity. So now I can replace the value of T using this 2 pi r by V, and hence I get the current expression is equal to E by T is 2 pi r by V, which is equal to EV, okay, not electron volt, this is electron, charge of electron, V is the speed of electron, by 2 pi r. So now we have the expression for current expressed in terms of charge, velocity and radius of the electron in its orbit. And further, one more important term is current, which is equal to pi r squared, and hence now I can get the expression for magnetic dipole moment. Magnetic dipole moment is generally expressed as small m, but for the hydrogen atom, or when I take the electron in its orbit, we express the magnetic dipole moment, the same magnetic dipole moment, not using m, instead using mu. Okay, yeah, don't, okay, it is mu L. Okay, I'll tell you why mu L. We'll express mu in terms of L. What is L? Angular momentum. Okay, we'll see what is that now. But before that, you should be clear. Mu L is the symbol that we will make use of to express the magnetic dipole moment of the electron in its orbit. So mu L is equal to I into A. Okay. This is nothing but dipole moment itself, magnetic dipole moment with a new symbol, because we are choosing it for electron and they are minute, radius and all. That's why new symbol. What is I equal to? I is equal to EV by 2 pi r. EV by 2 pi r into, what is the area equal to? Area is equal to pi r squared. Pi r squared, pi and pi cancels, one of the r gets cancels. So we'll be left with E of V r by 2, right? E V r by 2. So this is one of the expression, E V r by 2 is one of the expression for the magnetic dipole moment of a revolving electron in the hydrogen atom, where r is the radius of the orbit, p is the speed with which the electron move, and E is the charge of electron. Okay, this is an important expression for mu L, but we will not end it there. Instead, we want to connect this mu L to another familiar term. Okay, one familiar term to us, to which we can connect mu L, is the angular momentum of revolving electron. So what is angular momentum given by? Angular momentum L is equal to mvr, right? Remember this, r cross p, r into mv. P is not the electric dipole moment, first P use 1. Okay, r cross p, r is the radius of revolution, p is the linear momentum. Okay, since the angle between r and v is 90 degree, L becomes simply equal to mvr for the revolution. Okay, We know this, we can directly take this expression. Since L is equal to MVR, and now I want to express mu L, okay, this L is subscript, okay, mu L is one symbol. So I want to express mu L in terms of L. How do I do that? So what is the term missing there? It is mass of the electron, right? So let me multiply and divide the expression by m. So it is EVR into m, EVR by 2 into m by m. Okay. So it is mu L is equal to, look at this, MVR. What is MVR together equal to L, right? So it is E into L MVR, E into L divided by 2m. Okay. So once again, this is the final expression, that's fine. But look at this, here we have E is equal to charge of an electron, M is equal to mass of an electron, where both of them are actually constants, and the ratio is also a standard constant, ratio of them, E by M constant, E by M, right? So I can also express this as E by M times L by 2. In some references, they will also keep it as E by 2m into L. That's also fine. But this is the final expression. Okay, this is an important derivation. So this is the final expression for magnetic dipole moment of a revolving electron of hydrogen atom expressed in terms of angular momentum of the electron. Clear? So that's it. Here we have connected so many things. This is actually a charge, electrostatics. We discussed the properties of that, and that charge is moving. So this moving charge will give us the current. We got to know about the current, and this moving charge gives the current, and hence the current in the circular shape gives the magnetic field or magnetic dipole moment. Or I can call the same arrangement as magnetic dipole, and this magnetic dipole will have the magnetic dipole moment. I considered that magnetic dipole moment as mu L. That mu L is equal to IA. So we took the expression of mu L and arrived at EVR by 2, but we were not satisfied. We wanted to express, if there is a reason, particular reason, we'll get to know. We wanted to express mu L in terms of L. What is L? L is angular momentum of electron in its orbit, and mu L become equal to, after introducing L by multiplying and dividing by m, the final expression that we arrived at is mu L is equal to E by m into L by 2. Okay, this is the final expression and the end of the derivation. Thank you.